All right. Good morning, everybody. Let me go back in my notes here. All right. So we were talking about acids and bases. We talked about kind of 5 factors that we dealt with about acid strength, right? We talked about whether it's cationic or not. The atom identity. R for resonance, of course. Let me try that again. Induction and orbital type. So we saw these generally. Oh, no, you can see me. Okay. Generally in order. These will describe our kind of stability of your conjugate base, which, as we know, determines how strong your acid is. So, with that, that's kind of what we've covered so far. What's important we do now is we want to talk about kind of the purpose of all this stuff, right? We're going to see that there's a lot of acid-base chemistry that happens. And so it's important for us to know how to kind of predict an acid-base reaction. So kind of, good morning. Good morning, good morning. It's going to be important for us that when we talk about putting things together, when we're having an acid-base reaction happen, remember that means an H is being transferred, essentially moved from one molecule to another. I kind of hinted on this last time. Shane, not Sean. I love it. Is that something that you would get called a lot? Do people really make that mistake? That's pretty interesting. We saw that if we have our always really that's I thought it would be obvious. You have the E at the end. Yeah, okay, well, whatever. We saw that if we were to put this acetylide ion with ammonia, we're not going to get a reaction out. No protons are going to be transferred. But if we have the alkyne with the amide ion, keep that there, we are indeed going to get a reaction happening. And so we end up with our negative there, and we get our ammonia out. So we kind of saw that last time, so we do see a reaction happening here. Another way to write this would be as an equilibrium, right? We could say instead that we're going to end up... Why didn't I just copy the whole thing? That was silly of me. We can see it's an equilibrium, right? You know, reactions are reversible. We know this, especially acid-base reactions, especially when we're talking about weak acids and weak bases. These things can completely go whichever way they want. But we see here that our acid in this case has a pKa of 25. And our acid in this case has a pKa of about 35. It's probably closer to 38, I think, is a little bit more common. And so the reaction is going to absolutely go in the right direction, as in heading towards the products. If we want to kind of evaluate a Kc for this, PKC is approximately, I mean, we can just say it, we've got the pKa of our products over the pKa of our reactants for this sort of thing. And so we're looking at about, or is it the difference? Because these are logs. Whatever. Either way, let's say it's probably closer to minus, actually, because these are logarithms of product minus reactant. So we're looking at about 10 here. So, or rather a factor of 10. Let me just arrange this a different way, actually. Let's just do it this way. So let's say it's the K, Kc of your products, or Ka, over your Ka of the reactant. And so in this case, that's about 10 to the 10. Right, so pKa is the opposite, right? So we're looking at a factor of about a 10 billion fold here. So we're definitely going to get everything to the right here, because those pKa's are differing by 10 units. So we're looking at about 10 to the 10 difference for our equilibrium constant. So our products over reactants ratios, we're looking at about 10 to the 10. So big difference here. So we can see that this equilibrium is going to lie very heavily towards the products, because we're going to end up getting a higher pKa in our product side of this. So that's one way we can look at it. So one, we can just look at pKa's, and your reaction will proceed toward your higher pKa, whatever that might be. Let's see if we've got some. Let's see. Let's say we've got these two. No, I'll make it an SH. Let's see what we can do with this reaction. Well, if it's acid-base, we're just going to be moving a proton around. Oops. And technically, we don't need pKa's for this one to figure it out. We can do the pKa's after, just to prove it to ourselves. But essentially here, we can either compare the acid strength, which is what we would do with pKa's. We'd say, okay, well, it's going to go towards the weaker acid, because the stronger acid is going to overpower it, right? Stronger acid is going to win out, and so you're going to end up producing your weaker acid in the end. Or we can just take a look at the conjugate bases. We can see which side... Good morning, Cecily. We can see which side has the more stable conjugate base also. So you can look at which has got the strongest acid, or we can look at the conjugate base and proceed to it. So we're going to go to the more stable conjugate base as well. So between these two, if we're looking at the conjugate bases, those are these two. Hi, little dude. Want to come say hi? No, he's just standing there. Okay. Looking at those two, which one's going to be more stable? The one with the sulfur or one with the oxygen? Of the underlying compounds. Yes, so the thiolethane there is going to be more acidic, meaning that the one with the sulfur is going to be our more stable conjugate base. So again, this reaction should go more heavily towards the product side. This one should favor the products as well. If we wanted to look at the pKa's, we would look at our acids and head towards the higher pKa. That's option 1, if we knew the pKa. So that's why it's a good idea to kind of have this baseline every, I did it, every 5 pH units or pKa units. I would, say, you've got your carboxylic acids around pKa 5. You've got your phenol and thiols at pKa 10. Alcohols and water around 15. You have your alkynes at 25. Amines at 35, etc. The reason I gave you all those numbers is so you can have a general idea. We don't really need to know the exact number. For ethanol, it's probably like 16.2, and this thioethane is like 9.8, whatever. The point is we have a higher one on one side. We want to head towards the higher one. Alternatively, we can look at the conjugate base and go towards whichever side has the more stable conjugate base. So either one of those will help you determine kind of where the reaction is going to go if there's some uncertainty. All right, let's do a problem here. Here, I'm sorry. I'll be good with my benzene. I will draw them out. Okay. Let's take a look at this one. You can look at it both ways. Let's take a look at the conjugate bases first. If we're looking at the conjugate bases, let's apply our Cario idea. Neither is cationic. Atomic identity is next. They're both on oxygens. So next is R. R for resonance. One of these has resonance, perhaps. Looks like the one on the right can resonate, meaning that that's more stable. And so therefore, we're going to head towards the more stable side. So once again, apparently I'm drawing all of these as product favored reactions. Let's redraw that arrow. So again, we're going to go there. You could say phenyl alcohol, that's fine. Phenol is a portmanteau of that. So with the other side, though, we can look at the acids and say, okay, this is pKa of 10. This is a pKa of another 15 or so. So again, we're going to head towards the side with a higher pKa. So either way, find the more stable one, go there. Find the higher pKa, go there. They should be on the same side, so we're going there. Let's choose one that has a... Aha, okay. No, we're going to do it the other way. Okay, so here's one. And let's go ahead and pluck off that H. Plus our ammonia. So with this, let's figure it out. So let's look at stability first. I forgot my negative charge. Shame on me. Stability. Conjugate bases are the negative ones. I've drawn a counter ion for some reason. Let's just get rid of that. I don't know why I did that. We don't need our counter ions. They don't do anything. Chemistry-wise. So if we're looking at these, let's look at which one's more stable, our conjugate bases. First one, cationic. Nope. Next, atomic identity. Aha! They are on different atoms. We have a negative that's on carbon, a negative that's on nitrogen. Which one's better? Which one's more stable? Is it going to be this one or this one? Indeed. Absolutely. So we're going to see that this one is more stable due to atomic identity. It's more electronegative. It's in the same period as carbon, so we're going to go that way. And so this time, I actually rearranged this on purpose. So we're going to have a greater propensity to go in the reverse direction. Unlikely to go to the right. So with this, pKa of this is about 50. pKa here, about 35. So definitely we're going to be going to the left. Go to the higher pKa. All right. So that's how we can kind of worry about the positionality of things. So how we're going to see how this works. All right. How is that? If we were to draw a mechanism, by the way, remember, we're always going to start our arrows at a lone pair. That's how we get to the negative charge on the carbon. We've just plucked off that hydrogen, and now we have the extra hydrogen on the ammonia instead. That's the mechanism. That's what we mean by mechanism. In here, we've got the same idea. Lone pair is going to go grab a proton. The electrons from that bond, exactly how the electrons are flowing, and now we're going to end up with an extra lone pair on our oxygen. And so we end up with there. So that's mechanism. So those are the arrows that we use. Remember, always start at a lone pair or a double bond, and always end as a lone pair or double bond. So you end back on an atom or onto a single bond to make a double bond. Or triple bond, you could do that too. But that's neither here nor there. Okay, cool. So that's how we can kind of predict the products of a reaction, like predict which direction it's going to go. And so we can now work with that. The last kind of bit here that's minor that I want to talk about in this chapter is sometimes you have, depending on your solvent, some pKa differences within the same kind of functional group. So we can sometimes have solvent effects as well that affect our pKa's. Solvent effects has an E. So if we're to take, for example, these two compounds, methanol or T-butanol. You don't need to learn these names yet. You will actually later today learn to do that, so never mind. So for right now, suffice it to say that this is these are all methyl groups here. These are CH3s. What happens with this, and I'll in fact draw the other one the same way. When we deprotonate these, when we're dealing with polar solvents, we can have, for example, water is probably not the best choice as a solvent for this, because water is just going to go ahead and be attacked and lose a proton. But suffice it to say, bad example, but good example, because we all know about water's polarity, right? We know, aha, all those hydrogens are partially positive, and they can interact favorably with that negative charge to stabilize it a little bit. But, in fact, let me redraw this one a little bit more accurately. There, we'll make this a little bit more obvious. With this one, because of what is called, all these dudes, these are what's called Steric Hindrance. So things are blocking more water molecules from coming in. So we have this bulky T-butanol. It's bulky. It's got a lot of stuff on it. Those are preventing more water molecules from coming in. And this is called steric hindrance. So as a result, this T-butanol is going to be less stable because the solvent can't access it. So your solvent can help to stabilize things because you remember that water is attracted to positive and negative things. So the water is going to want to come in and interact, and that's going to help stabilize things. But if you've got a lot of stuff in the way that's preventing your water molecules from coming closer, that's going to make it a little bit less stable. And I think if we look at the pKa's here in water, the T-butanol is about 100 times less acidic. So pKa for this is about 16. It's about 18 here. Alcohols, again, generally I say 15. That's a rule of thumb. But we can see here that the sterically hindered, yes, you can say that. Yeah. So it just has stuff blocking the way. Water does not want to interact with methyl groups, CH3s, because they're nonpolar, right? So the water is not going to hang around there, and just things are physically blocking it off. We're going to see that this is going to be important when we talk about substitution reactions, because for something to substitute another thing, it has to be able to kind of wiggle its way in. And so we're going to see this idea about sterics. Actually, sterics are going to take a pretty big role in a lot of stuff that we do in this course and the next course. So we're going to see that many reactions are under electronic control, meaning they're going to go where electrons favor them going, as in they're going to go to the more positive side or whatever. And sometimes sterics will control what happens with the reaction. And so sometimes, no matter how electronically favorable it is to make something happen, just sterics, things that physically block it, can have a big impact. So to even make a reaction not happen at all. So we'll see that kind of OChem is an interplay of those two. So yes. Okay. Cool. Alrighty. So the book also has sections on leveling effects and Lewis acids. I'm not going to really worry about those right now. We're going to talk about Lewis acids more in next semester when we talk about reactions with aromatic systems, because we're not going to really be dealing with Lewis acids in this semester, so we'll talk about that later. And then leveling effects are more lab related, so sometimes your choice of solvent, actually in this particular problem, water is a pretty crappy solvent to use on these, because water is actually going to just react with them. And I mean, if we think about water's pK about 15, it's going to go ahead and react with these both and protonate them. So yes, there is some hindrance there. So if you're comparing these two molecules, here, let's look up water's actual pKa value. And we'll look up methanols as well. Data page. I hate looking up water on Wikipedia because it wants me to go to the weirdest things. Okay. Properties of water. Yes, here we go. pKa, solubility in water. I'm glad it is 13.995. So right. So pKa is about 14, we'll say. If we look at methanol, here I'll be as specific as possible. 13.995 there, and then pKa of the methanol is 15.5. We definitely do see this trend happening. So yes, you do have some steric effects because of the methanol. Yeah, you could use ammonia as a solvent, but the problem is ammonia is gaseous at most temperatures. So, yeah, you could. Though a better choice that would be liquid at room temperature would be T-butanol actually by itself. This is so if you had a mixture of potassium T-butoxide and T-butanol. T-butanol would be a great solvent for this because if it does react, it produces the same thing. So overall, there will not be any reaction. So this could be a good solvent for this guy, for that one. Or yes, you can use something that has a way higher pKa. You're probably not going to be able to get this to dissolve if you use like hexane or something, but hexane would have a pKa of 50, right? And so it would be an excellent choice as a solvent if you could use it. So, but we're going to see that often the conjugate acid and conjugate base work very well together because if they do react through leveling effects, they're going to produce the same things. Overall, no reaction happening. So, yes. Speaking of which, I should mention, you see here I put a potassium. I could put a sodium instead. I could put a lithium there. Doesn't matter. Counterions don't really do anything in organic chemistry. They're there to just stabilize things. They don't participate in the chemistry, so very often we can just ignore them. So sodium, potassium, lithium, pick your favorite, use it. And yeah, have fun with it. So those are not very important for us. So, cool. Any questions on kind of this idea of predicting the acid-base properties or side of a reaction, or about some of these acid properties we talked about, like any of the Cario stuff or the other ones? Any good examples we have here? Nah. All right. That's all I wanted to talk about with acids and bases. So, which is good because that means we can get a slight head start on alkanes because we have a lot to talk about, and I'd like to have more time for that chapter. If I've given them, yes. If they're not there, you don't need a counterion. So I think with some of like the nucleophile, electrophile questions, there's some lack of counterions there. So you don't need to put them. But if no, I'm just gonna say you can ignore counterions. So in general, like they're just gonna be there balancing things out, but they're not gonna participate in the chemistry, so I don't need you to indicate them. So don't worry about counterions. You're going to have enough stuff to worry about in this course, so let's take out some of the extra stuff. Alrighty. Alkanes, then. We're going to actually now start talking about some chemistry. No, it's more properties. Not really chemistry, but that's okay. This is our first kind of class of compounds, our first functional group. I say that with quotation marks because alkanes are really boring. They don't do much in terms of actual reactions. But these are fully saturated hydrocarbons. Those are what alkanes are. By saturated, I mean there are no double bonds in these. So, ta-da, there's an alkane. 4 carbons, some hydrogens on it. They follow the pattern of this chemical formula. However many carbons you have twice as many plus 2 hydrogens. So if this is C4, you're going to have H10 on it. Remember, we could have an isomer of this. Which has the same chemical formula. This is a constitutional isomer of this compound. So we can just do that. Hooray. Alkanes typically follow this, or not typically, they always follow this formula for their chemical formula, but that's not something we typically use because we see these are different compounds here. They're structurally different, and so structures are more important than formulas are, but they do all follow that formula. If you're putting cyclic alkanes, you're introducing degrees of unsaturation in there. And so, yes, you're going to lose 2 hydrogens for every time you make a ring. So if you have, for example, 3 rings here, you're going to lose 2 hydrogens per ring that you have. So if we see here, that's 18 carbons. You're going to have, in theory, 38 minus 6 hydrogens, so 32. Yes, but that's something we'll talk about a little bit later. We're going to stick with linear alkanes right now. These are also called aliphatic. I do not know where this word comes from, but that's okay. Aliphatic is the same thing as kind of what we're talking about here. These are going to be saturated hydrocarbons. Saturatic. No, that's not so right. Saturated hydrocarbons. Same thing. AKA alkanes. The first thing we want to do with talking about all these alkanes is to learn how to name them. And we are going to start by learning how to name linear alkanes. This is our first kind of foray into nomenclature of organic compounds. We're going to see there are a lot of rules for us. Nothing so simple as sodium bromide here, unfortunately. We're going to see alkanes are kind of our simplest functional group. So saturated fats have esters or acid groups on them, so they would technically not be alkanes. But they have large portions that are alkanes. Only 3. Okay, let me try that again. There we go. So, right, your fatty acids look like this. Am I missing carbons here? I'm totally missing carbons. These should have 1 more carbon. Whatever. This is some general fat. It's not a triglyceride, but it's some fat. Okay. With these, yes, that is indeed 2-methylpropane. Those bits, if we were to just have them without the rest of the molecule, those would be alkanes. We could call those alkyl chains, though, for a part of a fat. So alkanes, yes, cannot have oxygens in them. So that portion of that fat we call an alkyl chain because that portion just by itself would be an alkane. So, but the entire molecule is not. That would be classified as a triester. But we'll talk about that. So, first things first is we need to learn the kind of names for a number of carbons. So, the first thing we have. If we have one carbon, that's called methane. We'll learn all these fun names. 2 carbons is ethane, propane, so number of carbons tells us the name of the molecule if it's just a straight chain. Butane. And then finally we get into prefixes that we remember. Pentane, hexane, 7, 8, 9, 10. We're going to go all the way to 12. We're going to have heptane, octane, nonane, decane, undecane, and dodecane. So, these are the kind of standard names for chains of carbons that are linear with nothing on them but hydrogens. So, for example, this dude right here is butane. Hexane. I don't have to draw them so nicely. I can draw them all whatever way I want. Here, I'll go crazy. Why not? 1, 2, 3, 4, 5, 6, 7, 8. This is octane. Typically we do draw them zigzags, but we'll find out that all of these alkanes can freely rotate all they want. So, it might be located, it might look like this, or it might look like this. These are the same molecule. We're going to see that these molecules rotate and go crazy all they want. These are both pentane. So, here, I'll go up to the chart for a few more seconds here. These names you will be intimately familiar with. Hopefully just the first, honestly 2, 3, and 4 might be the only new ones. Although you've probably heard propane and butane before in your life. Oh yes, you will definitely want to. More important though is the prefix. Meth, eth, prop, but, pent, hex, hept, oct, non, dec, undec, dodec. Those are the important parts. We're going to see here that the ending of a name in organic chemistry tells you about the functional groups that are in it. If it's just alkanes, we end it with ane. So all of these end with ane. Monkeys eat purple bananas. I guess that works. Yeah, that would work. So that'll get you the first 4, and then the rest you should know. Like pent, right? Pent is 5. Pentagon, hexagon, octagon. You know all the others. Perhaps 11 and 12 maybe you don't. But 5 through 10 you probably already know. So I guess yes, MEPB will be your methane, ethane, propane, butane things. So yes. I mean, in terms of actually are you going to need to memorize them? You will. But you don't need to put any effort into doing that because you're going to learn them, because we're going to do so many problems that you'll see that they will already be in your head by, 2 weeks from now. So, because every name for every compound in organic chemistry is based off of these. There might be some substituents added, but for these just linear straight chain alkanes, those are their names. But very often we have substituents. Remember, substituents are going to be things other than hydrogen that are going to be stuck onto our carbon chains. So sometimes we might have something like this. We've got 6 carbons. Aha! But now I have replaced one of the hydrogens with another carbon. And so, this little bit here, I'll even underline this in blue. This methyl is a substituent on this carbon chain. And so, we're going to see that when we are going to learn how to name these, our very first rule is we want to find the longest carbon chain within your molecule. And so, I mean, technically we have options here, but I've drawn it in such a way that it should be obvious. But we could say, aha, I'm going to say this is this my longest chain here? 5 carbons long? No. In fact, it is indeed this. This is our longest chain here. Indeed. So we have a 6 carbon chain. That's going to be our longest chain here. If we are in doubt, by the way, I'm going to give you the rule, even though I don't have an example right now for it. We'll talk about it in a little bit. Kind of part 2. If multiple options have the same, are equally long, let's say, we will choose the one with more substituents. So we'll have an example for that. So I like your ideas, but indeed Kevin has already mastered it. So indeed, what we want to do is we are going to take this longest chain. Longest chain becomes the parent name of the compound. So this thing that had 6 carbons as its longest chain will have the parent name hexane on it. So we will call this, in this case, something hexane, where something will represent all of the substituents on this hexane. And not only are we going to list all of those substituents there, we are going to number the substituents. To indicate which carbon they are on. So, if we look at that molecule again, we have some options here. So we've determined that our longest chain is the one that's the zigzag. We have a couple ways of numbering this. We can say this is carbon 1, 2, 3, 4, 5, 6, following our chain, our parent chain here. Or we could number them the other way. We could say 1, 2, 3, 4, 5, 6. The rule here is give the lowest numbers possible. So we could, depending on where we start our numbering, we can start it from the left or from the right. We want to give the lowest numbers possible, what are called locator numbers. and we see, aha, that methyl group would be best. The lowest number we can give it is a 3. To say it's on carbon 3 of our hexane. Hexane has 6 carbons. We have a methyl group on the hexane, on carbon 3. And so this one will indeed become 3-methylhexane. We should not have any space here. So I'm going to... there we go. No space, but we say we have a methyl group on the 3rd carbon of our hexane. And that is how we name these. Notice we have this substituent name that's changed slightly. So substituents, so carbon substituents will change. You'll take the ane and make it eel. When they are substituents, you change their ending from ane to eel. So we have alkanes and we have alkyl substituents on them. Just like before, we have alkyl chains in our fats, wherever they are. Notice I had this alkyl to indicate they are substituents. So they are attached to something else. If I were to take now this, if we were to identify our longest chain here, we would see we have 2 options and they're equally good, right? We could say it's this one. In either case, we're going to get 6 carbons, right? If we choose to go in the zigzag, we'll also get 6 carbons. There's no difference between them. They're both going to have 1 substituent, and it's the same substituent, so nothing changes. Yeah. So we'll want to start numbering this. So we could start here, or we could start from the other way. I'm choosing to do it from here because I'm just showing you you can do either way. And so again here we're looking on carbon 3 is going to be our thing, and indeed that's exactly right. This one will be 3-ethylhexane. It's ethyl because this is 2 carbons, right? This is an ethane. A substituent, so we are going to call it ethyl hexane. 3-ethylhexane. Systematic. How about this one? I'm being nice for these ones. I'm going to make all of our chains really obvious, kind of what they are. Now we've got a couple of things on here. Our longest chain indeed has, we'll just say it's the one in the middle. Can number it from either side. Alternatively, I could totally have numbered it from the top one instead. Doesn't matter, because again, they're the same substituent, so I could choose either one. But here's the thing. So we have 2 options. Remember, so if you want to choose the green numbers, Kevin has already got the right answer, as always. If we want to go with the green numbers, we'll say methyl is on carbon 3 and ethyl is on carbon 4. If we go with the purple numbers, We'll have ethyl on carbon 3 and methyl on carbon 4. We want to, since these are both on 3 and 4, we can't make the numbers any different. They're both going to be 3 and 4, whichever way we number from. We want to do it then alphabetically speaking. So we say, aha, ethyl comes before methyl alphabetically. So we're going to give the lower number to the alphabetically first one. So alphabetically first. That's really a weird way of saying that. Indeed. So the preference here is alphabetical. So we're going to see that that's the case. Okay. In this case, yes, we're going to get 3 ethyl, 4 methyl hexane. And notice we have these hyphens in between as well. Those hyphens are just there to make things super clear that we have an ethyl on carbon 3, we have a methyl on carbon 4, no space, and then we have our parent name. So all of these are substituents. Now, remember as well that if we can make the lower numbers, in this case they were both 3 and 4, whichever way we numbered them, something would be 3, something would be 4. If there were a way to make them lower, that would take preference over alphabetical. So you always want the lowest possible numbers first. If there's a tie for lowest numbers, then we go alphabetically speaking. I want to say there's some things in the book that I wanted to go over with. Yeah, we can talk about these. Okay. Yeah. What was a good one? Okay, I thought there was some good example with numbering it, but that's about bicycles. Aha! Here we go. So, what are we looking at there? Okay, 7 carbons. Okay. And we're looking at... Okay. Here's another example. So, again, I'm being nice. Our longest chain is in the middle. Our options... or... And this will also show you what to do when you have multiple of the same substituent. So, if we look at our locator numbers, for green, we have something on 2, 3, and 6. For purple, we have 2, 5, 6. So, indeed, we are going to choose the green one because that gives us the lowest possible numbers. So you always are shooting for the lowest possible numbers. All right, and so it's always kind of your point of difference. So they both have something on carbon 2, but then the next one has something on carbon 3. So that's the one we're going to choose. The others have higher numbers, so we're going to choose always the lowest numbers from the first point of difference. All right, so the 2's were the same. So we move on to the next number and then choose the lowest one there. So if some hypothetical compound had, you had the options 2, 4, 7, 8, 9, 10, or whatever, and just making numbers up, 2, 3, 10, 11, 12, 13, or something, we're going to choose this one. First point of difference is what we're going for there. But let's not worry about that. because that situation will hopefully never come up. So we want the lowest numbers. That's what we're going for. So 2, 3, 6 will win. These are all methyl groups. And so the way we do this, as Kevin has indicated, we call this trimethyl heptane. One thing to note, this tri thing does not count for if we need to arrange things alphabetically. So, we'll do an example of that, but we're going to consider this to still start with M for purposes of alphabet. So, if we do the same molecule, I've added now a propyl group onto it. We always start with the side that's got more substituents on it. So we end up with lower numbers there. If we do this one, we're going to have, let's just write out what we have. We know we've got this kind of trimethyl business. And on carbon 4, we have a propyl group. And so once we kind of list all of our substituents out, we can then look at them alphabetically and stick them onto our name. So we see here we have methyl. Remember, tri does not count for alphabet or di or whatever. None of those will count. Prefixes do not count for alphabets for these di, tri, whatevers. And those would follow the same rules like di, ti, tetra, penta, all those sort of things. So we're going to call this, the M goes before the P. So we are going to say 2, 3, 6 trimethyl. I don't know how to spell methyl hyphen 4 hyphen propyl no space heptane. Did Kevin get this one? Yes, he did. So, very systematic. We want our lowest numbers possible. We can throw all sorts of fun substituents on. If we have something like this, we'll see that our substituents are closer to the left side. We would call this 3,3-dimethyl hexane. So, if you have two substituents on the same carbon, you'll use the number twice in your name. In this case, they're both methyl groups. But if I instead had, so I can't make it an ethyl, well, here, I'll throw in something else here. If I do it this way, I would say 3-bromo, 3-methyl hexane, for example. I guess this opens the door. I'll put in kind of a few more substituents that aren't going to kind of overtake us, just so we have a few more substituent names to mess with. So, common substituents. You'll have something alkyl, like a methyl group. You'll have halogens, which will take the names fluoro, chloro, bromo, or iodo. Those will be their prefix names. What other things can I give you that are not going to cause the end to change? Ethers. We can talk about that. Those would be something like methoxy, or ethoxy, or propoxy. Ethers are low priority, so they will not change our parent name. For example, if we have this, we would look at what's on that carbon. Like, aha, that is a methoxy. That's an ether. It's methoxy because we have one carbon on the oxygen. If we had two, it would be ethoxy. As in the part that's not part of our chain here. So we would do it this way. So we would say, aha, that is just 3-methoxyhexane. So those would be another kind of functional group that we might see as a substituent. If we look at more alkyl substituents, that are common. So we saw, here's just some carbon chain, okay, as substituents. We're going to see that if we are connecting our chain to the middle carbon of a propane, we commonly call this isopropyl. So instead of connecting as a propane, we're going to have, the entire thing. We would call this isopropyl. It's bound to the middle carbon of the propane instead of the end carbon to the propane. There. So that's a very common substituent. We have another one, phenyl, which is a benzene ring. Yes, it would be 1-methyl ethyl, actually. But we'll talk about that because we need them to both end with the eel ending. So phenyl. If you have a carbon and then a benzene, you can call this benzyl. If you are bound to the second carbon of butane, you would call this sec-butyl, secondary butyl. Is that 1, 2, 3, 4? Yeah, that's 4. If you are bound to the butyl, but now it's kind of weird like this, where it's kind of an isopropyl with a methyl group also, this is called isobutyl. So isopropyl had us bound to that middle carbon of the propane. Isobutyl is kind of the same thing, but there's a carbon in between that. So it's kind of like a methyl and an isopropyl at the same time. That's isobutyl. What other common ones do we have? Yes. Tert-butyl. Sometimes this is written S-butyl and T-butyl. So these are common alkyl substituents that are not just plain old straight chains. So, looking at some of these, let's do some examples. We could call this one. Again, I'm being so nice. I'm putting our chains so nicely. I could have labeled from the left. Doesn't matter, you can get 4 either way. You could call this 4 isopropyl heptane. Yes, good, good. It does, because now I'm throwing all of these unusual things at you. We've done so many simple ones. Methyls, ethyls, propyls, but now we have more and more. Shane, that's going to be something that you're going to see very often in this class. I'll explain a reaction. Seems okay. 2 minutes later, you're in the deep end. So these are just more substituents. So unfortunately, there's a ton of information. The best part, though, is this is the hardest part of nomenclature, is learning these basics. And once you do that, adding more functional groups on is not going to be a problem. This is the hardest part of naming, at least. So, 4 isopropyl heptane, that works. Though, if you really want, Kevin did suggest an alternative name, which is just as acceptable. We could have called this 4. I need to write the 1 there. I need to learn to spell as well. Methyl, ethyl. What is this? Heptane. You could write it this way as well. And by that, Kevin's writing it as kind of this. We have a substituent on our substituent. It gets so much better, doesn't it? So, if you have a substituent on your substituent, you could name it like that, using parentheses. We're indicating, well, we have an ethyl substituent, 2 carbons, and on the first carbon, closest to our main chain, is a methyl group. Here's another example. So let's say I have 3, 2 chloroethyl pentane. We can draw this one. In fact, in this one, there's no other way to name this molecule. This is the best way to do it. Is that going to be this? 5 carbons. 2 more. No. Not pentane. Let's say hexane. Yeah. Otherwise, we'll have some trouble because then our chloro is actually part of the longest chain. So, gotta make it a little longer here. So, if you draw this, going from name to structure is easier. We're gonna see, because you can number it from whichever side because you already know what you're gonna do. So hexane, 1, 2, 3, 4, 5, 6. On carbon 3, we have a chlorine on the second carbon of an ethyl group. So let's draw the ethyl group first. I shouldn't have. I need to do heptane. Sorry. Because again, we're gonna mess with our longest chain that way. So we have to keep our longest chain as such. And in fact, I can't even put it on carbon 3 because that's going to mess that up too. Now it's on carbon 4. Don't you love all this crap I can do? Just keep messing with things. Oh, don't you worry. Don't you worry. We are going to have so much fun with that. Alright, and so this is going to be what this compound will look like. So we have our heptane. Oh, don't worry. Here, let's do it. And we've got, so kind of, if we look at our ethane, those are the 2 carbons of ethane. We always have to start our chain, or our thing, closer to our parent chain. And so that's why we're going to have it that way. If we wanted the chlorine on the other carbon, this would be 4,1-chloroethyl heptane. So we're going to need that. All right, because that's on carbon 1 now of our 2 carbons that are sticking out. So substituents within substituents. All right, so per the request, all right, here's some fun stuff to do. Some of those are really ugly lines, aren't they? Look at this methyl, it's all terrible. All right, so is it undecade 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11? Indeed, blah blah undecade. So that is a good first step. Undecade. That is a very good one. Undecade. Yes. Where's our longest chain? We're lucky. So, longest chain is going to be in the middle, or it could be here. I'm going to just start from the side. This could be our longest chain. Okay. That's our longest chain, right? Either one of those. How are we going to choose? Well, the rule is we choose the one that has more substituents. They have the same number of substituents. Right? So if we look here, carbons 3 through 11 are the same. So we can ignore those. Those substituents are all there. We see, though, that we both have something on position 2. And the rule is that we choose the alphabetically superior choice. So bromo is going to come before isopropyl, so we're going to go with the blue numbers first here. So the blue numbers will be our longest chain, and that will be our numbering system as well. So the blue ones will win. Okay, because bromo is alphabetically superior to isopropyl. One thing to note. This is fun. There's so many rules. I love it. Iso and cyclo do count alphabetically. but T-butyl and S-butyl, the T's and S do not count. So iso and cyclo count, tertiary and secondary do not. We really did, didn't we? Well, this was, I think, Jackson's request, right? Something with 200 substituents. Let's go ahead and do it. So, just for right now, isopropyl will be an I for our alphabetical purposes. Let's just see what we have. So, let's just go from number 1 to number 11 and write down what we've got here. So, we have 2-bromo. Carbon 2, we have a bromine. Carbon 3, we have an isopropyl. Carbon 4, what's that? What's on carbon 4? That is a phenyl. So you see here, the least of your worries is there a bromine on that phenyl group? If it were bromophenyl, it would look like this. Ah, cool. Okay. So that's the phenyl. On carbon 5, we could say methylphenyl, but let's not. Let's say benzyl, because that is an accepted name. So again, you thought butane and propane were going to be the worst of your worries. No, look at all these. These are going to be more of your friends. So here, let's throw another one. No, let's not. Okay. You could do methylbenzyl, but you would need parentheses for that if you want to do it. And it would actually be methylphenyl. No, benzene. So, yes, good idea. So, we could say 5-methylphenyl. All right, so we could do that. But benzyl is a little bit easier for us. We understand benzyl means there's one carbon in between the benzene and the main ring. So it means it's kind of one carbon offset. So if we wanted, we could say 5 parentheses methylphenyl. We could. But it's a little easier to say benzyl. So we'll do that. I'm going to move down. Move this stuff out of the way. Okay. On carbon 6, we have a methyl. On carbon 6, we have a methyl. Carbon 7, nothing. Carbon 8, fluoro. Carbon 9, 2 methyl groups. So 9-methyl, 9-methyl. Okay. So, here we go. We know it ends in undecane. We just have to arrange all this stuff alphabetically. So, that's all it comes down to. I mean, this molecule may seem terribly complicated, and it is. But it's all about, can you identify the substituents? Rather, can you first identify the longest chain? That's going to give things the lowest numbers. And then after that, can you name all these substituents and then throw them in alphabetical order with their numbers? That's all it is. So looking at this, benzyl is going to come first, alphabetically, then bromo, then fluoro, then isopropyl. Remember, the iso does count for this. And then we're going to have all of our methyls. And then we're going to end with the phenyl. So, now we just have to write it. So, oh my gosh, this horrible isopropyl thing is in my way. Okay. So, here we go. the name. The first one is benzyl, so 5 benzyl, 5 benzyl, then 2 bromo. Then what's our third one? Fluoro, 8 fluoro. Then after fluoro comes isopropyl. And then we have 6, 6, 9, 9 tetramethyl. And then 4 phenyl. Oops, left out. What was this? Even undecane. Isn't that fun? Amaze your friends. You can read all of these names. We should do this more often. Yes, this is the only question on the exam. That's it. Just name this 20 carbon nonsense. So, I'm not going to start talking about cyclic compounds today. Yeah, honestly, that's the hardest part, is just writing the damn thing. Figuring everything out is not that bad. Especially, I mean, we have time now. We can say, oh, let's go look at our list of substituents. Okay, let's see what we have here. Oh, we had that isopropyl and the phenyl and the benzyl. Right, so it's just learning the names. That's not too bad. But yeah, putting it all together is somewhat of a chore. So, I understand that. I think what I'll do, though, is get your next homework ready so you can start putting some names for things. And I'm going to give them to you in different arrangements. So sometimes you're going to have skeletal structures like these. Sometimes you'll have the carbons written out. Sometimes you'll have the hydrogens written out. And we're going to... I have to have you, unfortunately, have them both ways. While the skeletal structures are universally used by professional chemists and anyone who's teaching organic chemistry, the ACS exam decides to put carbons out there. So they will write these out. CH2, CH3, CH2, CH2, CH2. So they'll keep rings like skeletal, but they might write out something like, if we were to draw that, I don't know, this molecule here, they'll do like, so you still will need to kind of like, it's terrible. I hate these. They take forever to write, but you will still need to be familiar with these because, again, unfortunately, the ACS exam, which everybody must take, because that's what, in order for classes to transfer, that's what we have to do. And it's the same case if you were taking this at a four-year university, you'd have to also be looking at these molecules, but again, nobody teaches it this way. If you want, I think it's a good idea to, though hopefully this one's not too bad. You can see there's 7 carbons and there's 2 carbons coming off of it, but so there's one for each subject, of course, though usually just general chem and OChem. So though they do have ones for inorganic, analytical, and physical chemistry, as well as biochemistry. So they have 6 exams total. So general chem, OChem, those are the main 2 that people take, and then there's 4 more for the special ones. We didn't take one for 111 because I didn't have to. according to our course outline, I could give you my own exam. But for 113, I did have to, so it's the way it is. But for organic, we do. I think I have the option to give an ACS exam for this class, but I have to do it for the next class. So because of that, I don't want to be like, okay, it's a week before your final. By the way, now learn all of these in these carbons instead of skeletal structures. So these will still be peppered throughout your OChem experience for that reason. So, sorry. Would that I could get the ACS to get this in their heads. For whatever reason, Klein, our textbook uses... Actually, I have one of my old textbooks around. This is the textbook I used when I took OChem. And all of the structures are drawn that way. So, you can see here, they're all drawn this terrible way, and I hate it. So, at least linear structures. So, terrible. I think it's the worst way to do it. I like Klein. I chose Klein because Klein is in agreement with the rest of science. So, if you look at any paper published for chemistry, which is how we communicate our findings to each other through peer-reviewed papers, they're all using skeletal structures because they're better. These are clunky. Let's suffice it to say, we like clean structures. The cleanest structures we get are skeletal ones. Could you imagine if we had to draw out all the CHs for this thing? It would be a disaster. It would be horrible. It would be very hard to read this molecule. So, but I don't know why the ACS still does it with... Well, they might have changed it. I haven't taken an ACS exam in years, but... well, hold on, let's see. I have the preparatory guide for your ACS 8 OChem exam. Yeah, look at these. Look at these horrible structures. They're not quite condensed, so they unfortunately do it either way. So these are all linear, but here, let's see if we can't find some more that are less terrible. Yeah, so... For example, like number 7B or whatever, if you look at this, like look at these. So you see they definitely are these kind of, those structures, you'll see. So unfortunately ACS does it this way, but they typically give you easy molecules to work with. As you see, these are all 2 or 3 carbons, they're not terrible. So unlike these 11 carbon structures I'm giving you here, so unfortunately. By the way, this is something that's normally available to you in our classroom, but we don't have a classroom, so it is in my house. Normally I'll let you guys use this to take pictures of and stuff, but intellectual property law will not allow me to do that. The ACS does sell these, by the way. They're $25. If you want, share it with your friends, but I didn't say anything like that. Yeah, so just something to keep in mind. Yeah, cool. We'll come to the final exam discussion later on. What's it called? Just say like ACS Organic Chemistry Guide. Honestly, that's something to look at. So, does it even have an ISBN? I don't know if it's like an actually... Oh, it totally does. What do you know? Wow, there's 24 editions of this. Yep, so I cannot reproduce or transmit this by any means without written permission from the publisher. So, that is what I am bound by. So, but yes, I think just again, ACS exam organic chemistry guide. Honestly, put that into Google. I'm sure you'll get the hit there. And they in fact as well have practice exams online that you can take, and they'll grade it and everything, and you'll see the answers and they have feedback and all that. I think that's also like $25, but they only let you do it once, so you can't share those with your friends. So, you can't use them together, unfortunately. They let you take it once, and so you can't really use it together. Unless you take the exam together, but then that's kind of also bizarre. So, but anyways, if you just like go to the ACS exams website, it's there. So, yeah, cool. Anyways, on Monday, we'll continue talking about cyclic structures. We'll name cyclic compounds, bicyclic compounds, polycyclic compounds, I suppose. And we'll start talking about how to visualize these molecules and how they rotate and interesting stuff like that. So if you are still kind of on the fence for getting your molecular models, next week is when we're going to start using them. So you'll want to get them by then. In fact, I don't even know where mine are. That's a problem, but I'll figure that out because it'd be good for me to draw these molecules or to have them to show you at least on video. So syllabus has the link for getting the model kits that I like to use. So that's there. Okay. Anyways, that's it. So Monday we'll continue. I'll go ahead and put this up, and I'll post your videos. So enjoy your weekends, and we'll see you next time. So take care. Enjoy learning your nomenclature.